Welcome to the webinar, Maximize Mine Profitability with a Safe, Sustainable, and Flexible Design Strategy, sponsored by CIM Magazine and Dassault Systems Geovia. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine. But before we get started, I'm going to just do a little bit of housekeeping. If you joined the webinar by computer audio, to make sure you have optimal audio, select the computer button. If you joined by phone, make sure you've selected the phone button. If you have questions during the webinar, click on the little question mark here and type them into the GoToWebinar control panel question box. The questions will be held until the question period at the end, but please feel free to type in any questions as they arise. Now I'm going to introduce today's presenters. Glenn Barlow, who is one of our speakers, who is Geovia Industry Process Expert Director at Dassault Systems, and Richard Gawthorpe, who is Geovia Industry Process Specialist at Dassault Systems. Now, without further ado, I'm going to switch it over to Glenn.
Wonderful. Thank you very much. So what I'll do is I'll just share my screen here and we'll get going. Is that coming through okay for everyone on the organization side? Rich, you can see it okay?
Yes.
That's it.
Wonderful. Okay. So yes, thank you very much for your time today and for your interest. We're going to take you through a few different bits and pieces here around our strategic life of mine planning tools. To begin with, I'll hand over to Rich to walk us through the first steps. Over to you, Rich.
Thank you. As Glenn stated, in this discussion, we're considering the arena of strategic mine planning. And by that, I mean the process of taking a resource model and carrying out optimization, design, and schedule in order to evaluate the profitability and define the best option of extraction of that mineral deposit out of the ground. Now, this process is controlled by parameters which are used to simulate the realistic situation of extraction and to generate the best net present value of the operation. But really, is the best NPV the best option? Is that the optimal option? What we're suggesting during this discussion is that there is further work that can be done. And we're going to be talking through a work process which describes how one can add on to the optimal answer that comes out of the process, but one can actually define something that is a little bit more robust, something that takes into account fluctuations in the parameters and fluctuations in the assumptions that have been used in that process. So let's move on to the next slide. And let's have a look at the current situation. What do we do today? Basically, we take in a resource model, which defines to our best ability the material within the ground. We then use that and apply a series of parameters, which are assumptions about the future mining situation that will incur over the life of the operation. They'd include economic parameters such as mining cost, process cost. They'd include your product price, and then physical parameters such as mining capacity, process rate, process recovery. In addition, geotechnical parameters, slope configurations, and that sort of thing, and geographical parameters such as exclusion zones. And then more recently, we've been starting to look at ESG type parameters such as carbon footprint and electricity and water consumption. So as you see, as you understand, there are a myriad of different parameters that are used to control the output from the strategic mine plan. But this only gives us one answer. In the traditional format, one would do simplistic sensitivity analysis because of the amount of time that this whole process takes. So we'd be looking at 2 or 3 of the different parameters and varying those over time in order to get an understanding of the sensitivity of the ore body to changes in our mining situation. But what we're suggesting here is that there is a better way of doing this planning, where we actually look at formalizing the planning process in such a way that we can carry out many different scenarios in order to understand the robustness of the plans that come out. And by robustness, I mean their exposure to potential risks in the future. So if we move on to the next slide, I'll talk us through how we define this workflow. So what we are going to be discussing is linking together the surface mine planner, which is the optimization and scheduling engine that we use, with the surface mine designer, which are all controlled by the parameters which are input into the different tools, such as mining capacity, process capacity, recoveries, etc. So once we've set up the base case, we then have an opportunity to carry out what if scenarios. And by using something called Process Composer, which sits over the top of this whole process, we're able to set up a matrix of variable parameters. So working from the base case parameters, we're able to create this matrix of different process runs. And because these are then run as individual projects, we've got the ability of running these instead of end to end, which would be done in the normal, in a linear fashion in the normal application. Because this whole process is cloud-based, we have the opportunity to utilize multiple CPUs. So we can run literally thousands of scenarios in the time it takes to run only a handful. And then this generates a huge amount of data, which then needs to be post-processed in order to change the data into information which will allow us to make business decisions based on the variability that comes out of this workflow. So what it does is it opens up the areas of probabilistic analysis and moving into stochastic analysis. So on to the next slide. And over to you, Glenn.
Thanks very much, Rich. So Rich has given you a bit of an overview there to what that process looks like, but what I wanted to do was dig a little bit deeper under the covers and to show you a little bit about how we do that and what we do with it, okay, how we're able to achieve those runtimes that we've talked about there. If we're looking at performing tens of thousands of different schedules, exploring the entire scenario space, well, then we've got to do it quickly, okay? Now, cloud technology and cloud computing gets us so far. It gives us extra power, extra capacity to go off and model things, but it's not a substitute for good algorithms. It's not a substitute for efficient and fast algorithms that can help us to solve problems in a better way. And there's no point in brute forcing a poor answer. Okay, so we need to make sure that we have algorithms that generate good results to begin with, so that we can then vary those inputs and generate better outputs to begin with. So what I wanted to do is just give you a bit of a background into how we arrived at where we are today. So to begin with, in strategic mind planning, in traditional tools that are out there, most people will have heard of the Lurch-Grossman algorithm. Now, the Lurch-Grossman algorithm is quite an old algorithm by modern standards. First published in '64, first commercially available in the Whittle product that we have within our product suite in 1984, and it became pretty much the standard for generating the ultimate pit shell. How deep, how wide, what material you're going to take, applying your costs and applying your revenues against that, and generating the output. It's good. It worked very well for us for a number of years, but it's essentially an older algorithm, and so it has limitations. In 2008, a new algorithm was published called pseudoflow. Now, pseudoflow solves the same problem as Lurch-Grossman. It just does it in a fraction of the time. It uses superior technology and superior algorithm to allow us to model it not just as a pricing problem of one block connecting to another block and out, but to refine that problem and to use technology that comes from other areas, okay, to model it instead as a flow or network flow problem. So it's basically a rethinking of the problem, but what it does do is produce the exact same results. Okay, there is no difference between the outputs that you could see in a Lurch-Grossman derived final pit shell and a pseudoflow derived final pit shell. But pseudoflow does it very, very fast. And that's important because, as I say, when we want to do this solution space of tens of thousands of problems, we need it to be quick. So that's the advantage of using pseudoflow. But both of these are algorithms to solve for the ultimate pit. They don't tell us what's going on inside that pit in terms of scheduling. It doesn't take into account the application of time, or not in the standard implementation of these two. And so you then need to apply within that ultimate pit shell some form of scheduling engine, some form of scheduling algorithm. Now, in 2003, Whittle Consulting launched what they called their Proba Global Optimization. We then took that and implemented that in 2010 into Whittle as what we call our simultaneous optimization, or SIMO module. Now, what this is doing is it's solving that scheduling problem within that final pit. But it's not just looking at what is the best time to mine that block to meet your requirement in this period. No, it's optimizing across the entire schedule for the entire life of mine. And it's not just looking at that block in isolation, it's looking at that block in combination with all the other blocks that are available. So what it means is that when we run a global optimization or simultaneous optimization, we're not just saying that that is a good time to mine the block to meet the target today. We're saying that that is the best time to mine that block across the entire schedule, okay? Optimizing across the entire solution space. And we also optimize, as we do that, our stockpiling strategy, our cutoff strategy, our capacities, both our mining capacity and our processing capacity. We do all of that in one step by achieving this. And so what we're able to do with that kind of solution is to effectively get a much better MPV than you could achieve by looking at the problem on just one period at a time and sequentially scheduling it one period at a time. So you get a much better result for it. It's not just the best time to mine it for this period, it's the best time to mine it full stop across the entire schedule. So it's very good, it's a very effective set of algorithms, the simultaneous optimization. The problem with it is it's slow. And the problem with it is because of the solution space that it's solving. Okay? As you start to add more attributes, more constraints, more variables that you want to optimize, the linear programming problem starts to explode. It grows exponentially. Every additional attribute that you add to it makes the problem space enormous. And so trying to solve that rapidly becomes a problem. And we start to go into the older days again of waiting for optimizations to run overnight or leaving it for a couple of days to get a result. That's not viable for us because, as I say, we want to put more attributes, more constraints on our models. We want to look at not just capacity problems, not just cutoff problems. We want to look as well at putting in ESG targets. We want to look at constraints around water consumption, around electricity consumption, around acid consumption. We want to add in additional attributes and constraints that allow us to change the way that things are modeled in terms of mining width, in terms of how we group blocks together to make a practical or more practical output. And so this solution of using simultaneous optimization in its traditional approach starts to run out of steam. Okay? We basically start to fill the capacity up too much. So we get a very good answer for the number of attributes you can put into it, but we can't model the entire solution space the way we want to. And we were stuck there for a while. What's come about in global optimization terms since then, though, in 2010, the Bienstock-Zuckerberg algorithm was published. Okay? Now, what the Bienstock-Zuckerberg algorithm is able to do is it's able to relax the problem, okay, so simplify the problem to a degree. And by simplifying that problem, it's able to achieve for us very rapidly an upper bound of where we can expect things to be. What's that theoretical maximum that we want to achieve to? And once we know what a theoretical maximum is, well, that's a target. We can then fit to that target with our own heuristics or with our own optimization tools that we have on the top of it. And that is effectively what we did in 2023. We launched our own algorithm here called the GMX algorithm. Now, the GMX algorithm incorporates the Bienstock-Zuckerberg algorithm. It combines the concept of simultaneous optimization, so optimizing everything in one step, blending everything in one step. And it implements as well pseudo-flow to allow us to be able to do some of those optimization and those pit problems rapidly and quickly. So effectively, it gives us the power of this simultaneous optimization solution with the speed that we get with the BZ algorithm and combines it together. So, well, what does that look like? Okay, well, we've done a lot of different studies on this. We've tested it against all known published results. Anyone who's published a result on the through literature of how they've solved these kinds of problems, we've tested ourselves against those. And what we saw with using our solution to it and using the GMX solution for it is that we're able to massively reduce the number of iterations. So we take ourselves from the original BZ algorithm solution to a well-known mine planning problem called McLaughlin. We take ourselves from 79 iterations down to 16. Okay? That gives us a 6 times reduction in the number of iterations, and that gets us to an optimality gap against that original BZ algorithm on the 6th decimal place, which is more than enough precision for anything we do in mine planning. So what we're able to do with that algorithm is have the speed, have the improvement performance, solve for the entire solution space, but do it very quickly and very rapidly. When we tested it against our CMO algorithms, we were getting moderate increases in the MPV, but we're delivering it in 130 times faster. So it's massively quicker. And all of that is useful, not just so I can hit the button and get an answer in one go, because I don't want one answer. What I want to do is feed it with tens of thousands of different variables, tens of thousands of different scenarios, and have it output for me all of those different answers so I can explore fully the entire solution space, and I can start to analyze the risk in a much better way. But I can't do that if I don't have speed and if I don't have quality in my optimization. So that was our targets. That's what we aimed to hit, and that's what we've been able to do with this new tool set. If you want to know more about the GMX algorithm at any point, we've got a couple of white papers published. We'll be happy to share those with you. If you contact us afterwards, we'll put a link for those so you can see them and look into them in more detail. But that's what we've been working on this side. So algorithms are all fun and interesting. They're nice to know about. They have to be there. They're not really the bit that most end users interact with. Okay, the algorithm has to have a good interface. It has to have a good front end to enable you to be able to use it in a practical way, and we have to be able to populate that algorithm with the right variables that we want. So what I'm going to show you here quickly is just a very short video showing you what it looks like in terms of the software itself. So within the software itself, we launched this within our 3D Experience platform. Now, the 3D Experience platform for us is a way of bringing together data from various different sources, from various different disciplines. Okay, it has within it tools for optimization and life of mine planning like this, but it also has tools inside it for geological modeling, has tools inside it for civil design, has tools inside it for collaboration and lifecycle management, has tools inside it as well for mine planning. Okay? With the aim being that if we can model everything inside of a single system, well, then we can start to do some very interesting things. Then what we can start to do is look at how we connect these different parts of our total process together. We can start looking at how we can cascade and automatically update things that are downstream from the beginning. And so the vision within Geovia and the approach that we think the industry should be taking is to connect everything as much as possible, so that when we see a change in our drilling data, we automatically see a change in our geology model. When we see a change in the geology model, it automatically updates our resource model. When our resource model changes, it updates our optimization. When our optimization updates, it changes our design. When our design updates, it gets fed back into our scheduling system to produce the final schedules. So it's our vision to bring all of that together, and the 3D Experience platform is our solution, our methodology for doing that. Because we believe that things are better when people can understand it. We believe that things are better when everyone can view the same data. So to give you just a quick view of what this looks like, we've got here a range of different controls over our toolset. We've got the ability to define our slopes, our phases, our scheduling constraints. We've got the ability in here to define our locations, to define our commodities, to put in place here our processing paths and the recoveries and costs against those processing paths, in much the same way you do in most life of mine planners. And we've got the ability then to go off and run it and to generate our different pit shells, our different final pit shells for analysis. Then we can display them, then we can view them, and we can start to do our analysis. We can start to put in geospatial constraints against it, protection zones, rivers that we don't want to go through, safe and practical areas that we can't mine through, and we can apply costs to those, and we can let the algorithm go off and tell us when should we move into that area, how much would it cost, when's the best time to upgrade capacities in our plant or in our fleet, when's the best time to purchase into a certain zone, okay? Or indeed if it's not worth going into at all. All of these are controls that we use to make more practical and better looking life of mine schedules. We also have the ability to build in here our phase generation. So once we've got that ultimate pit, we then need to break it up into phases that we want to schedule through, phases that we want to model through. So we've got an intelligent set of phase generation tools, which group blocks together in a sensible manner, which look to make coherent mineable phases with minimum mining widths, with smooth edges to them, that allow us to advance from one stage to the next in a logical progression, but also to do it in the most economic way. We've got tools to look at different mining directions, so to test various different mining directions for us and to see how they compute and what they do, because the mining direction is critical. Okay? When we're calculating the NPV, the ore that you bring to the plant in the early periods is worth far more than the ore that you bring in the later periods. So the optimization tool has to be able to look at that and say, okay, what's the best direction to mine this? Okay? You can enforce a direction if you choose, but the tool also can suggest to you what the best direction will be by testing the 8 cardinal directions and testing off of start points that you supply it with. So the solution is able to build that practical phase generation. We're able to generate sensitivity analysis on it as well, so we can throw in various different parameters. And when we generate in this way, we will get a single answer out of it. At this stage, we're still generating one answer for one fixed set of inputs. We can vary some of the inputs, but we're still generating a fixed output for a certain set of inputs. And then we can feed that data into our designer, which will go off and generate our more practical designs here to make sure that what we're actually saying we can mine on a block basis is actually mineable when it comes to building more detailed designs, okay, and running with our capacities. And then, of course, we generate various reports and outputs that we want to use elsewhere. Okay. So this is the toolkit. This is the solution that we utilize for it, okay, to solve those problems of when should we be mining a given block, which direction should we be going, what capacity should we use, what uncertainties do we need to be aware of. Okay. So once we've got those initial parameters, those initial phases set up, well, then we want to go to the next step of it. We've got something that's economic, we've got something that looks sensible on a block basis, but how do we know it's actually practical? How do we know we can actually mine it? To do that, you need to build a design. And to do that, I'll let Rich walk you through this next step.
Okay. So, as Glenn said, the process of generating the optimal pit is carried out within the optimization environment. Once we have an understanding of the pit shells from a global point of view are going to be our design pits. We need to bring those into the design environment, and this is where we harness the power of parametric design. Now, as it suggests, parametric design uses parameters to define the design. But what do we mean by parameters? So what I'm referring to is three areas of focus. One is the input parameters themselves. Now, those are in the optimization environment, things like your metal price and your mining cost, etc. In the design area, there are a myriad of design parameters, such as bench heights, berm widths, face angles, haul road inclination, haul road widths. And all of those things are parameters which are input into the design and are then used to control the design. But also, parameters can accept other parameters as inputs by using user-defined formulas to actually calculate new parameters from the parameters which have been established, perhaps pulled out from the geological model. So we can use a formula to define a regression curve to define the parameter of plant recovery based on the grade of the material in the ground. So this is another way of parameterization. Secondly, what we're talking about here is associativity. This is where we actually use objects, three-dimensional objects, as parameters in the process. This means that, the example we're going to show after this is where we actually use the output shells from the optimization engine as parameters fed into the mine design package, which means that if we update our optimization shells or we update our topography, we're able to automatically feed that new information into the design. And because the design is controlled by parameters, the design will be automatically generated based on those parameters. Now, in order to keep a handle on all of this connectivity, we've put together a data model which allows detailed tracking of the data. It allows us to generate a single version of the truth so that all of the inputs are linked together in an understandable format. So if we run through the whole process, the geological model is linked to the optimization. The optimization is linked to the design. The design is then linked to the schedule. But in addition to that, we're able to enable in-depth collaboration, and we're able to use life cycle control and revision control to organize and to administer the linkages between all of these different versions so that one can actually step back and do comparisons between different scenarios within the system. So it's the combination of these three areas which give parametric design its vast power. To illustrate that, if we move on to the next slide then, we've got a short video here which is showing the linkage between the optimization and the pit design. So if you have a look at this, this is the output from an optimization, which is showing a series of different phases within an optimal pit. Those are held within the block model, converted into shells, which are then used to control the design. The design is created using a series of parameters. The first set of those parameters defines the bench elevations and the bench heights, which are then used to apply the geotechnical parameters of berm width and face angle. In addition to that, we define the configuration of the road through width and inclination, and then we apply all of those parameters to the body that's going to be designed. So we then generate a series of benches at a defined height using the geotechnical parameters that we've defined earlier. This then uses the shell as a design guide and applies the geotechnical parameters in order to generate toes and crests, which define the pit shell from a design point of view. So this is all based on the shape of the shell. So within the designer, there is a series of tools which allow you to define your positions of your haul roads, and within that, we're able to define the haul road in a practical position within the design itself. This is done automatically using the tools. So we move away from the situation where we have to incrementally design from the bottom up or from the top down. The haul roads themselves have the ability to, or we have the ability to move the haul roads from one position to another. We can put in multiple haul roads. There is an automatic switchback definition, which allows us to change the direction of the haul road at a particular elevation without having to edit the design by hand. So that is linking the crests and berms to the position of the haul road. We update the position of the haul road, the design updates itself. So once we've established a potential pit design, we can generate a surface in order to look at that. And then using the revision control, we're able to say, right, okay, that's our first design. Let's move on to scenario number 2. Let's have a look at what happens if we change some of our parameters. So in this situation, we're setting up a new scenario, which is based on the first scenario, but this is going to use a new set of parameters. And the parameters that we're going to change here are the optimization parameters. So in this situation, we're going to go back into our optimization, and we're going to we've created a new version. So then we're going to go back to the optimization. We're going to change one of the fundamental parameters. Here we're going to change the metal price. We're going to increase the metal price by 20%, and that's going to give us a new set of shells. So as you see here, the output now has increased to the side. So we've got a larger optimized shell. So now we can associate this shell with, this shell is now associated with the pit design, which is brought in from the previous scenario. So rather than having to go back and redesign the pit, using the same design decisions, we can come up with a brand new design automatically on the fly, which gives us an incredible turnaround speed, and it gives us a huge power. And then because these are two different versions within the data model, we can then do direct comparisons of those two designs. Here we're showing from a graphical point of view, but we can do the comparison from an analysis point of view, where we actually have a look at the material within the different designs and make a comparison between the two scenarios. So this as Glenn spoke about before, this is not only giving us a power, it's also giving us a time saving in order to carry out the multiple scenarios that we've been talking about. Next slide.
Thanks very much for that, Rich.
Okay.
So what Rich was showing there is how we can apply practical constraints onto our life of mine optimization. So the life of mine optimization went through and generated based on blocks, but blocks are not what we use in the real world. Sloped angles between blocks are not true outputs. So what we've done there with that solution space is to add in and bring the design component and the scheduling optimization component and put them together. And it means that we have a continuous feedback loop between those two solutions that allows us to make a change in one place, have it cascade and update the design, and then have that feedback in as part of our schedule for the final output. And so it's one of the ways that we use of making sure that we've got a safe and practical schedule, because we've got that ability to feed it back in. Okay? Without that, you have a human in the middle. Okay? And the human in the middle will have to make the clicks, do the generation of the design, create the output. We want to remove that as far as we can and automate that, because, as I said earlier, if we're going to do tens of thousands of scenarios, well, then I can't have someone creating tens of thousands of designs. It will take too long. We won't be able to solve the problem in a reasonable time frame. So instead, by automating this and making it a parametric setup instead, as we feed that change in of our parameter, we can vary any of the parameters on our design as well, and we can generate the outputs very rapidly so that we can check them and see if they're practical and see if they're sensible to use. So when we start to look at this problem from a multi-scenario standpoint, then we start to want to use things like our Process Composer tool. So the Process Composer tool allows us to set up these different designs of experiments. We're able to put in here what is the parameter that we want to change, what values do we want that parameter to take, how should it feed from one location to the other to create the outputs that we want to achieve. Okay? So we can use here a range of different loops and flow structures to build out the experiment. And then once we set it off to run, we tell it to go off and run and to achieve its output. Okay. We can then look at how we analyze that output. So we want to get not just one optimized solution, we want to be able to look at a wide range of it. So in this case, we're setting some parameters here. We're telling it what the input parameters, what the output parameters are. We're going to see in here what the ranges of those different values are and how they distribute to each other. We're going to tell it if it's a objective and if we want to maximize it or minimize it. We're going to set a priority for it, whether it's a must-have or an important priority or a low priority. So in this case, we're looking at carbon emissions and water consumption, but we're also optimizing on cutoff grades, processing capacities, mining capacities, and initial capex. It will go off and run for tens of thousands of scenarios. In this example, we've done about 650, just to make it nice and quick. But you will be presented with all of those different scenarios here, and it will rank them based on the weighting that you apply to the objectives. So if we tell it that MPV is the most important objective, then it will rank them based on MPV, then based on our secondary objective, our tertiary objective, our quaternary objective, and so on and so forth. So we're able to have the solution tell us what it believes to be the best results, but we can also dig into this and analyze it ourselves. So we're able to come in here and look at everything, or instead we can use the sliders that we have on the left-hand side here to change the ordering of it, or we can use that to change the filtering of it and to show us just certain results over other results. So if I'm saying, I'm looking here at different MPVs, different processing capacities, different capex, show me what we've got here in the lower end of the capex. And it'll filter out my results here and show me what we've got. Show me what we've got here in the lower end of the carbon emissions. Okay, well, it'll show me here what we've got on those lower ends. The aim here is to look at forest, this enormous setup of different scenarios, and pick our alternatives, so that we have not just plan A, but we've got plan B and C and D and E as well that we can use as we see fit. We can then look at comparing these to each other. So if I select, say, 6 different scenarios here to make a comparison on, I'll put them into my basket. That's what this little icon is along the side here. So I'll add those scenarios to basket. And then once I've set them in the basket, we can then see how they rank against each other, these different alternatives. And we can compare them to each other and say, look, in terms of our objectives, this is our top objective. It does our best performance of MPV, does our best performance of carbon emissions. It's good in water consumptions, but CapEx is a little low in terms of target. Okay, this one has a much better CapEx utilization. Okay, but it performs more poorly on MPV. It performs more poorly on water consumption, for instance, or it performs badly on carbon emissions. So we're able to look at these various different alternatives and pick what is the best alternative plan. Okay? These have already passed through the optimization. They've already passed through the design stage. It's all been brought together for me and then presented to me in this fashion. So I can then make an informed decision about what is plan A and what the rest of it should be. We can change the weighting of any of these objectives. We can change objectives if we want to, and it will serve up to me what those best results are instead. And I can change here the parameter weighting just so I can see what the differences are on them and see what that does. And it will give me here my output. So I can then look at what the recommended scenario is. I can pick 1 or 2 off of this, and I can share it with other people within my group so that we can all have input to it, and we can all agree, yes, okay, this is a good result or this is not a good result. We also have some advanced visual analytics in here. So when we're dealing with this number of scenarios, we need to have good ways of charting and graphing them and controlling them. So I've got in here a 2D scatter plot of MPV versus its score. If I want the top MPV, I'm going to go this way, and I'm going to select those by using a lasso to draw around them. And it's then going to show me those different scenarios. What are these different alternatives? Where are they out of all of my possible scenarios? How do they look against each other in terms of my objectives? And so I can use this to see what we want. This whole view can be customized. You can change the different charts that you want to have on it. You can look at a range of different statistical analysis around it. We can look at things like 3D surfaces. We can look at things like correlation plots. Okay? But essentially what it does for us is it allows us to solve for that very large set of problems and to better understand what it looks like and come through with it. I'm conscious that we're in our last 15 minutes, so what would be nice now is to try and run you through a couple of case studies here. So I'll hand back to you, Rich, just to do a quick run through of one of these, I think. I don't think we'll get through our full case studies, I'm afraid.
Okay, yeah. So this is an example of a case study that was performed a little while ago, where basically we were trying to define the optimal direction of mining. Now the situation normally is when one has one's nested pits, you have the onion peel development of the pit, which you can see is illustrated in that shape, which is designated no direction. So what we did here was we set the system up to run in each of the 8 cardinal directions with the pit development north around the compass. And we ran a series of pit optimizations on that, and compared the net present values that came out of those schedules. And what we found was that there was, depending on that direction, a variation of the NPV that was developed. And this allowed us to then move on to the next stage of picking out the best 3, which then we could move on to the design phase, and it gave us a way of homing in on the optimal answer. Okay, Glenn, if you move on. And then this was taking that one step further, was once we had those 3 mining directions, where was the starting point? Where should we start mining? So we basically put a grid of points over the ore body, which was made up of 200 points. We then analyzed the different directions with those points, and we managed to generate 1,600 scenarios, which ran in about 15 hours. And that allowed us to increase the NPV from the lowest to the highest by as much as 5%, which shows the power of being able to do this type of analysis. Okay, Glenn?
Okay. I'm going to do this one very quickly because I think we're almost out of time. But one of the things that we spoke about as well in here is when we explore the solution space, we want to look at what is a robust plan. Okay, so it's easy to achieve an optimal answer, but if we get changes, if there's a risk encountered, and there's risks in everything we do, okay, the answer in life, as in mine planning, is there is no right answer. There's only compromises. Okay, and we have to compromise in different areas to get the result that we want to get. So if we look at changing one parameter and changing another parameter, we will find an optimum point for both of those parameters, but it may not be stable. A slight change in one might see us lose a significant amount of value as we drop down the side here, or a change in another one might see us in a more stable location. So what we aim to do within this type of multi-parameter analysis is to not just find the largest possible value, but also analyze around that point to find the stable location, something that is resistant and robust to changes that you might see. What if the grade isn't as good as we say it is? What if we're not able to get the recoveries that we think we're going to get through our mill? What if we're not able to achieve the production capacities that we say we're going to have? Okay? So we have to be able to look at a range of different parameters to try and see how that works, and to try and minimize that risk to us. So we've done a couple of different case studies around this in the past, looking at different capacities, looking at different cutoff grades, looking at different destinations, different capex inputs. But ultimately, we are trying to, as I say, not just get solution A, which might be the optimum value, but a risky option. We want to know as well what's option B, C, D, E, and F that might result in us having a more robust schedule that's more easily achievable, and therefore more likely to actually deliver the value that we say it does. So that's the kind of work that we've been doing. Those are the case studies that we've been working on. We have these published as well, so if you'd like to know more about these case studies, please let us know. We'll be happy to point you in the right direction. We're down to the last 10 minutes, so I'll stop there, but hopefully this has been something of interest to you, and you're seeing how we're trying to improve the way that we do our life of mine planning and the way we do our strategic planning.
Great. Thank you, Glenn. Thank you, Richard, for that interesting presentation. Just a reminder to everybody to please type in your questions in the GoToWebinar question box. It's underneath the question mark on your control panel. And just to kick off the question period, I'm going to ask you, in your analysis, can I change the weight that each objective has? And can this be changed over time? And like, how much can I customize and define the objectives?
Mm-hmm. Rich, do you want me to take that one?
Yes, sure.
Sure. So the weighting can be changed at any time on the objectives. Okay, so at any point we can change the impact of a given assessment to see how it changes the ranking of our different scenarios. We can change it at different times if we wish to through the optimization tools. We can change the capacities at any time. But what we try to set up is a cohesive set of parameters that has all of our different options, and then we can pick from those options as we go through. Okay? So the answer is yes, it's part of the configuration. For the analysis later on, it's very much just a case of changing the priority and saying, if this is a higher priority, what does that do? Pick from the entire field of answers and tell me which one's the best for that particular objective at that particular time.
Okay. In terms of associativity, how easy is it to track the steps the platform has taken to get to that final outcome? Can I see the cascade effect you mentioned from changing something in the resource model to the pit layout, for example? Can I see that cascade happening?
Mm-hmm.
I'll take that if you like, Glenn.
Go for it, Rich.
Absolutely. There is a graphical representation of the linkages between the different objects that make up the association between the different stages within the analysis. So that can be graphically represented as a flow chart. So you can see directly how information flows from one scenario to another, how it flows from one process to another. So that is part of the data model that we've established on the platform.
And it's vital for auditing. So
yes,
when you're sat there looking at an output, I want to be able to see which resource model was it? Was it definitely the right resource model? Has there been any update to that resource model that I'm not aware of? So having that linkage between all of our different object types in here means that we can also perform audit on it to go back and say, right, this is my end result, but what is it made up of? And I never lose those connections. That's a problem that we've got in other solutions in the past. That how do you know you're using the right data? How do you know you're using the right version of things? So being able to go back through that full linkage of how we got there is really important.
Okay. You mentioned parameters should not be circularly dependent, but there is lots of inherent circularity in mine optimization. Can you detect and avoid situations that don't converge?
Yeah, that's a really good question. So the answer to that one is a bit of a complex answer, but I'll try and simplify it as much as I can. So in the majority of cases, if we try to position a circular argument to it, so A is updated by B, B updates C, and then C updates A, that's a failure condition for most of our tool sets because you don't have that capacity to do that. What we've got is workarounds for it where we don't update A, we update a revision of A instead, so that we have it as a new input to that process to go round. So there are checks in the software automatically to stop those things from happening. And the workaround for it in our process is to generate an additional revision of that output input, that A result that is both an output and an input to our next process. But it's something that comes up quite a lot. actually, as you start to work through this, because you start to think, okay, so that's an output, that's an input. I'll put that together and see how it works. Okay, and then you sit there and go, actually, no, that doesn't work. I can't do it that way. I have to do a slight twist on it to make it come through. So the tools are there to help assist with that, but it is entirely possible to set yourself up in a loop, and the tool will sit there and say, no, you can't do it. Okay, please make a modification here.
Okay. How about, I have another question here. Does the mine planning consider the parameter of variable market demand fluctuations?
So that's, again, quite a nice, interesting one. Do you want to do that one, Rich? Or?
No, you carry on. It's fine.
Okay. So demand-based planning is a really cool scenario to try and model up, because it's highly variable, and variability means large problems, it means complex problems to solve. So we can try and simulate that demand-based planning, setting up different outputs that we want to have, setting up different parameters that we want to feed into it, but it's not a immediate optimization setup. We have to feed it with the range of answers. It's not something where we can tell it it's a live stream of information, go and generate your own outputs. Okay? So it's something we can cater with, but it's more of a simulation of a live feed of demand-based planning, rather than being sat there saying I must have a live feed of that data, if that makes sense. Hopefully I've answered that.
I think it's more applicable to perhaps shorter term planning and shorter term scheduling than specifically to strategic scheduling.
Yeah, we are forward looking in our schedule generation, not backwards looking, and not at the point looking either. So it's all forward looking for what we do.
Okay. Have you ever integrated the mine to mill approach in your technology? And if yes, how have the results been in terms of mine profitability?
I probably need a little bit more detail on what that is. Mine to mill means different things to different people, I'm afraid. We do run the process through all the way to what is the final product produced out of the mine or out of the mill. And we do have the way of modeling what that looks like as we go through. But it is a strategic planning solution, not a tactical planning solution. What I mean by that is that we're not haulage constrained or anything like that, for instance. It's a case of saying these are what we expect to have as our outputs. This is what will generate the best MPV across those outputs. So again, forward-looking solution, we have to feed it with the inputs that we expect it to have, and it will then tell us the output.
Okay. Does it take climatic conditions into consideration as a parameter?
Ooh.
I think one has to take into account those sort of environments in the definition of the parameters themselves. Unless one can say have a linkage between rainfall and say production rate, and perhaps use a variation of rainfall over a period of time, and use some sort of formula to link that to the production rate coming out of the pit. That's quite an interesting application. I think there is a possibility there, because again, it's an input parameter being used to control another parameter. So I think that that would be an interesting exercise.
Yeah. Effectively, it's a throughput capacity limit that you have in different areas. So you'd be sat there saying, if you're in the tropics, for instance, during the rainy season, you have to half load your trucks. So therefore, you have to have a lower capacity for it. And you'd have that using our period definition. So when you put in any parameters, you've got a period fluctuation on it. You can sit there and say, at this time in the period, we'll have this, at that time in the period, we'll have that, and to model that through. Likewise, in colder climates, you might well say, actually, when it turns winter, we get a much better capacity. We can load the trucks a little bit more. When it's in the summer, the haul roads are a bit more mushy, and we don't want to load the trucks quite as full. So it would be capacity constraints. It'd be seasonal capacity constraints, which we should be able to model using the formulas on the period builder.
Mhm.
Okay, unfortunately, it looks like we've run out of time. Any questions that were entered by our attendees into the question box will be forwarded to the presenters, Glenn and Richard, so they're not just lost in the ether. I'd like to thank you, Glenn and Richard, for this very interesting presentation. I'd also like to thank all of our attendees and ask that you please fill out the short survey that pops up on your screen at the end of the webinar. A link to the video recording of this webinar will be emailed to you tomorrow, 24 hours from now, basically. And for more online presentations like this one, visit the CIM calendar of events on cim.org. Thank you very much, and we hope to see you at our next Solutions Exchange webinar. Have a good afternoon. Thank you.
Thanks all.
Thank you. Bye.